So it's third quarter, and to save yourself a lot of points on tests and save your ears from a lot of miss-out yelling, we made this video to show you a couple very often missed things that you learn in the third marking period and to review some stuff for you. So I'm going to talk to you about stoich and how to recognize stoich in some problems that are really often missed but are really not that hard.
I'm also going to talk to you about a few stoich problems and then also just review the VSEPR chart because that comes back in some of the AP questions, and also just some miscellaneous information that we tend to forget at this point in AP chemistry.
And then I'll just be covering the periodic trends and some easy tricks to remember them.
Alright, so this problem asks you to find the concentration of the propanoate ion. Even though this comes from a buffer problem, you should be able to recognize that it's not an icebox or any kind of equilibrium problem for question AI, because it's not talking about change in anything. Nothing's added, there's no change in concentration, volume, anything like that. So you should be able to recognize, since you're given grams here, grams in the problem, and a volume in the problem, you should be able to use stoich to find the concentration. So first, you need to recognize that it's a 1-to-1 mole ratio from the propanoate ion to sodium propanoate. So then you can just do 1 mole of the propanoate ion over 1 mole sodium propanoate. Then multiplied by the molar mass of sodium propanoate, which is 96, and then multiply that by the given grams, and then that gives you moles of the propanoate ion, and divide by liters here. In the problem you're given 50 milliliters, simple conversion to 0.050 liters, and then you use the simple molarity equals moles over liters to find the concentration of the propanoate ion. Now we'll just put this final answer on the screen for you for a second, and then we'll move on to another stoich example. This problem from the 2010 AP test asked you to find how many moles of sodium hydroxide were added at the equivalence point. So this is one of the most missed stoich problems. A lot of kids try to do an icebox or something like that to find this answer, and it doesn't work when it's really just a very simple stoich problem. So you have to recognize that when it's asking you to find either moles or a volume like milliliters or liters of something added at the equivalence point, it's just a really simple stoich problem. So you're given 0.100 liter or 0.100 molar sodium hydroxide. So since molarity equals moles over liters, that gives you this to start out your problem: 0.100 moles NaOH over 1 liter. And then the most important part of this problem, after you recognize that, is to recognize to use the titration curve given in the problem to recognize how many milliliters of sodium hydroxide were added at the equivalence point. So by looking at the titration curve, you see that there were 40 milliliters of sodium hydroxide added at the equivalence point, because that point is given, and that's where the titration curve forms a straight vertical line. So at that equivalence point you have 40 milliliters, which is 0.040 liters, because you need your liters to cancel out. And then when you do that math, that gives you an answer of 0.0040 moles of NaOH. So once again, the most important things are to recognize that this is just a simple stoich problem. Don't try to do an icebox or anything like that. And then the next important thing is to be able to use the titration curve to see how many milliliters of sodium hydroxide are added at the equivalence point, and use that volume right here. So then your liters cancel out and you're left with moles of sodium hydroxide. Alright, we'll put this answer up for you and then give you another example. One last important thing to remember about this problem before we give you another example is that if you're asked to find the volume of something added to reach the equivalence point, you simply flip this around and do liters over moles. And then that way you'll be left with either milliliters or liters of the species that you're asked for to find the equivalence point. And it's still just the same simple stoich problem.
Okay, so this problem should look familiar to you guys because it was on the Honors Chem Final Exam Review Packet from last year. And this is a problem that you might actually see on a buffer problem, but it doesn't require an icebox. It requires simply a stoich problem. So since it says it contains 1 acidic hydrogen per molecule, you can figure out that it's a 1-to-1 mole ratio between the acidic hydrogen, or the acid, and the NaOH. But the key here, if you're going to write the balanced chemical equation, is you don't want to break down NaOH or HX, which what we'll call the unknown acid, because while it may not screw you up in this problem, it will screw you up in other problems because of having 2 moles of H+, which you don't want to have. So we're writing the balanced chemical equation as NaOH plus HX yields H2O plus NaX. And now the key is here to never break down this. If it's, obviously break it down for a buffer problem, but for a stoich problem you don't want to, because the two moles of H there can sometimes screw up the problem overall, and you just end up having the wrong number of moles, and you can't do the balance the moles properly. So in this case, it's just simple 1-to-1 mole. You're going to do 1 mole of HX over 1 mole of NaOH. And then this is the key to recognize here, is that 1-to-1 mole ratio, which you can get from the balanced chemical equation, because you have 1 acidic hydrogen, therefore you can determine how many moles of the acid there would be. Now you're just going to plug in the information that you were given. So what we did here is we just plugged in the given information. Obviously you take the molarity in moles over liters, multiply by the given liters, and you get an answer in moles. Now this problem asks for the molar mass of the acid, and since you're given grams, you're going to use the simple grams over mole to find molar mass. You're going to plug in the given 2.314 grams. All over the point we found for the moles. And that gets you an overall answer of 194.8 grams per mole. And that's how you do that problem, recognizing how the acid is balanced 1-to-1 with the sodium hydroxide because it's specified there's a 1 acidic hydrogen.
So I'm going to be covering the periodic trends, which at this point in the year, you're not really tested on this that often, so it's really a common thing to forget. So if you think of this as a periodic table, you have your ionization energy that increases as you go across, as well as the electron affinity, and both of those decrease as you go down also. Atomic radius, that increases as you go down and decreases as you go across the periodic table. And one very common exception to this is the ionization energy of magnesium versus aluminum, which is very common as you go down. And with this, the ionization energy of magnesium is actually greater than aluminum, which goes against the trend. And this is because the 3s orbital in aluminum does a better job shielding the other electrons than it does itself. So it is actually easier to remove an electron from aluminum than magnesium. And there are a few other exceptions that they're frequently tested, but this is one of the major ones. Also, with electronegativity, it doesn't just follow one concrete trend. Just remember Frankel-Briggs pH, and you should be good from there. Alright, one last thing with the periodic trends that is often commonly missed is when you're dealing with the parent atom and its ion. Particularly, we'll be doing sulfur versus the sulfur ion. So with this, the sulfur ion has a greater atomic radius or ionic radius because there's more electrons, obviously. So the electron cloud is larger, therefore increasing the electron-electron repulsions, causing the atom or the ion to be greater in size. And the sulfur 2- ion also has lower ionization energy because the electrons are more spread out, and therefore they feel less of a pull from the nucleus than in the parent atom.
Okay, another thing that is sometimes people screw up on is VSEPR. And while the VSEPR chart itself is pretty straightforward, and I highly recommend that you guys remember that for this part in AP, especially with marking period finals as well as review quizzes, because it's a common problem on there, and it's common on the AP test as well. So those are easy points, but sometimes people get tripped up on how to determine if something is polar or not. Now, there are 3 simple ways to determine if something is polar: the type of bond, the shape, and the share of electrons. Asymmetrical share is polar, where a symmetrical share of electrons would be nonpolar. Also, CH bonds are always nonpolar, so C2H4 would be nonpolar just because of the bonds. Now, there's one example problem that we got tripped up on this year, and I'm going to do it for you right now, and it's comparing these 2 compounds. And it's saying which one is polar, which one is not polar. Well, if you look at first glance, you would think that both would be nonpolar because they're both AB4 and tetrahedral in shape. But this is I wouldn't call it an exception, but you have to recognize something else here. And I'm going to do it right now by drawing the Lewis structures for you. So for this one, there are 20 electrons total. And this one has 32 electrons. We can now draw this out. C down to F, down to F, and then the lone electrons around both the F's. And then it's bound to the H. Now what's key to realize in this one is that it's asymmetrical itself because of the 2 different types of bonds that we have here. Not bonds, but 2 different elements that it's bound to. It ends up making the compound itself asymmetrical, and therefore it is polar. So you have to, that's a very important one to look for. Ms. Ott likes to quiz a lot of people on that one, so watch out for that one. That would be a good one to review. And then for this one, it's simple C bond to the 4 F's. I'm not going to draw the lone pairs in there, but they each have their own 6 electrons of lone pairs. And this one is obviously all the bonds, all the things it's bound to are the same. They all bond to F, and for that reason, it's nonpolar. So that is why CF4 is nonpolar and CFH2 is polar. I'll show you guys. Take a quick look at that question. And then one more thing to realize about polarity is dipole moments. The AP test likes to ask a lot of questions about the dipole moment, as sometimes little parts to questions. And dipole moment is simple, just follows polarity. The more polar the element, the higher the dipole. Non-polar element wouldn't have a dipole because it's not polar. So just remember that dipole goes with polar, and you should be good. Okay, just some miscellaneous information that we felt was important, and you guys should review, just because it'll show up on review quizzes, and a lot of people tend to forget. First, Kelvin can never be 0 or below 0. It can never be negative. You always got to remember that. Always. It's so important, and it's easy to remember. And then also with Kelvin, whenever you're dealing with perv nert or anything that contains an R or constant that has Kelvin in the constant, in this case it's 0.08206 liters times ATM over mole K. Since it's got K, you have to do any temperature data when you're putting it into the equation as Kelvin. And also I would just say as a rule of thumb, you don't really, there's no times when you would have to do Celsius, per se, except maybe for some colligative properties, but that's not on the AP test. Also, helium has 2 valence electrons. Maybe there's one question that gets asked about that the entire year, but everyone gets it wrong, so it's important to remember. Now, something that people tend to trip more up on and is more common that is asked as a question is oxidation numbers. So I'm going to put 2 examples up on the board, and I'm going to explain why the oxidation numbers are as they are. Okay, so OF2, simple. O is always -2, right? Not in this case, because you have to remember, since F is more electronegative, it is always +1. It's always -1. F is always -1, not +1. My bad. Anyways, since this is -1, O2 can't be -2 if we're to balance out, so O2 in this case has to be +2. This is an exception. I would look over at it because you might see it a few times. KO2 over here, this is +1 since it's a metal, so in this case O2 has to be -1/2 because it's paired with a metal and creates a superoxide. That's another exception. Always remember, it's not always -2 when it's with a metal or creates a superoxide. So these are just 2 exceptions that they're very helpful to remember because you'll probably see them, so I'll probably put them on a test or review quiz. Let's just see if you've been reviewing your material. So I remember these 2, and just remember that the exceptions for O2. Okay, now one more exception with oxygen that I know for a fact myself on one of our tests was hydrogen peroxide. In this case, H is +1, so O2 can't be -2, it has to be -1. This is also a very common exception that they like to test a lot on to try to trick the students. So I would just remember, make sure you know this exception as well, and you should be fine.